Here we have another sample problem to let you familiar with how to calculate the surface integral. So here it says a non-uniform electric field given by this expression. Okay, so E is 3x I vector plus 4j hat plus 4j hat. Okay, so this x means, okay, so E is an E field. Okay, so which means that it is defined on different spaces. Okay, so this x is the x coordinate of that point. Okay, so for example, for this point x is 0. For this point x is 3 meter. For this point x is 1 meter. Okay, so this E field is not uniform. It's not uniform. It's non-uniform. Okay, so this x-axis component is related to its x-axis coordinate 跟它的 x 坐标有关 and then plus 4j is is a constant. Okay, so ijk, so j is the y-axis component. Okay, so and then here's the Gaussian cube as shown in figure. Gaussian cube means we assume this to be the Gaussian surface. And then it is a cube. Okay, 所以是一个正方体的一个高斯平面。Okay, E is in n over c, and then x is in m. And then what is the electric flux through the right face? Okay, 那一个正方体的话有6面嘛，所以这个是问你右手边那一面。Okay, the right face, the left face. Okay, so the next page we will calculate for the left face. So for this page, we try to calculate the total flux on the right face. Okay, so here we try to calculate the integration of E dot dA. Okay, so we just put a subscript here, R, to stand for the right face. Okay, small r. Okay, so in this case we have integration of r and then 3x and then 4j. Okay, so something like this. Okay, so you may ask, why it suddenly turns out to be like that. Okay, we may consider something like this. Suppose we on the right face. Okay, so this is it is a plane. Okay, so for this whole plane, the dA should be pointing to the right side. It is perpendicular to the plane and then pointing outside of this cube. Okay, so dA always point to the right side. So in this case, this dA is actually dA times, this is x-axis, so we put it as I hat. Okay, and in this case we have E dot dA, to be 3x I hat plus 4j hat, and then dotted with this dA and then I hat. Okay, so this is a dot product. 就是点积或者是内积，那就是一个乘法。乘法的话，我们就可以分配率。Okay, so you can use the distributive law. Okay, so it will be like 3x and then dA and then I dot I. Okay, so this one dotted with this one. Okay, so this is the magnitude. This is the magnitude. So put it in the front, and then we only have this I dot I for the first term, and then for the second term 4j and then times dA, and then we have j dotted with I. Okay, so we need to know this dot product. Okay, so we can simply draw a small table. Let me see. We have I dot I to be 1, and then we have j dot j to be 1, and then we have k dot k to be 1, and then we have I dot j to be 0. j dot I to be 0, and then we have I dot k to be 0, and then we have j dot k to be 0, and then we have a k dot I to be 0, and then also we have a k dot j to be 0, something like this. Okay, so we all together have 9 combination. Okay, we have ijk for the xyz component, the unit vector for the Cartesian coordinate. Okay, so if we need to pick 2 to have dot product and then can be repeat, so altogether we have 3 times 3, 9 combinations. So if this unit vector are dotted with itself, then it will be 1, and then if one is dotted with another one, then it will be 0. So there will be 3 ones and then 6 zeros in this table. Okay, so this is really easy, but this is just unit vector notation code in the Cartesian coordinate. So that sometimes you don't need to care about the figures. Okay, if you can write the vector in the unit vector notation. Okay, for some of the selected problem, we will ask to answer in the unit vector notation, which means using the ijk. And in that case, if you can really write the vector in the unit vector notation, we can just consider something like this, and then you just need to remember what is I dot I. I dot I is 1, so we have 3x dot dA, and then j dot I is 0, so nothing. So it turns out to be 3x times dA, so we put it here, and then it already becomes a scalar. Okay, so actually for the right face, x is actually this 3m, so which means that we are integrating 3 times 3 for dA, and then we are actually integrating a constant, so which means it turns out to be 9 times integrating dA over the right surface, so which means it is nothing but the area of this square. Okay, and then the length, okay, we have 3 meter for this point and then 1 meter for this point. Okay, so the length of this cube is 2 meter. Okay, so the area is 2 square, so it turns out to be 9 times 2 square, which is 36 nm square over c, so this is the answer to the first question. Any question to this? So this is the dot product. This is the dot product for the unit vector in the Cartesian coordinate. So you can easily remember all this, and then we can use it for this calculation. And then this integration is easy because it is like we try to integrate a constant. Okay, so even though the E field is not uniform over the whole space, but when we consider the right face, okay, so in that case, x is a constant only across this right face. Okay, so in that case, we are still integrating a constant, so it turns out to be multiplication. Okay, so if no problem, then we move to another one. So here we try to consider the left face. The left face is this one. Okay, so similarly, we can have dA pointing to the left side. So in this case, it is dA times negative I hat. And then we can calculate E dot dA, which will be 3x and then I hat plus 4j hat, and then dotted with dA and then negative I hat. Okay, So we can do it more quicker. So which means that here we have I dot I will be 1, but here we have a negative sign, so it turns out to be negative 3x. And then for the second term, j dot I will be 0, so it turns out to be negative 3x dA only for this case. Okay, so here we are trying to calculate integration E dot dA for the left surface. So we put a L here. So here we have an integration of a negative 3x dA, 3a for the left surface. Okay, so here for the left surface, we have x to be 1 for this surface. X is always 1, so which means that we put x equals 1 here. So it turns out to be negative integration of 3 times 1 and then dA for the left surface, and then this one is a constant, so it turns out to be negative 3 integration of L dA. So this is the area of the left surface, it is still 2 squared. So negative 3 times 2 squared, which is negative 12 and m squared over c. Okay, so this is for the second part. So this is similar to the previous case. The only difference is that for the right face, x is 3, so we put in 3 here. And then for this case, x is 1, so we put a 1 here. And the other difference is that for last time, for the right face, dA is pointing to the right side. So here we have a positive value, but here dA points to the left side, so we have a negative value here. Okay, so for the third part is consider the top face. For the top face, okay, so for the top face, dA is pointing upward. So this is x-axis, this is y-axis. Okay, so this is dA times y-axis ijk. So this is j hat positive y-axis. Okay, so here we have a E dot dA to be 3xi hat plus 4j hat, and then dotted with dA j hat. Okay, so we also distribute. For the first one, we have I dot j will be 0. So we have a 0 here plus here 4j dotted with this one. We have 4 times dA, and then j dot j will be 1. So it turns out to be 4 dA here, okay, for the top surface. So here we are calculating integration of E dot dA for the top surface T. So so here we have integration of T and then 4 dA, 4 dA. So it is already a constant. And then we put it outside, 4 times integration of dA for the T for the top surface. And then similarly, this is 2 squared. So 4 times 2 squared, which is 16 and m squared over c. Like this. Okay, so this is about how to calculate the E dot dA for a non-uniform electric field. And then also, we try to learn about how to calculate this dot product with the unit vector notation. So this is called the unit vector notation. Unit vector notation 就是单位向量的表达。Okay, so far any questions? 有没有问题？有冇問題？ Okay, so let's move on. So here comes the most important part in this chapter called the Gauss law. Okay, so we have already prepared many stuff for the electric flux. So here we can try to use the electric flux to talk about what this Gauss law is. Okay, so here it says Gauss law relates the net flux phi of an electric field through a closed surface, a Gaussian surface, to the net charge Q enclosed that is enclosed by the surface. It tells us that epsilon naught times phi, okay, equals Q enclosed. So it's just a multiplication. It's just a multiplication. Something similar to F equals MA. F equals MA is a product. Okay, so here, similarly, okay, on the left side we have epsilon naught, which is the permittivity constant, what we introduced in the beginning of chapter 21. Chapter 21, where we talk about the Coulomb's law. Okay, so this time, this epsilon naught appear by itself, not something like 1 over 4 pi epsilon naught. Okay, so it is just epsilon naught here. And then phi will be the net flux. Phi will be the net flux of an arbitrary Gaussian surface. Okay. Of course, you need to define a Gaussian surface first, and then you apply the Gauss law to this Gaussian surface. So for a given Gaussian surface, you can of course calculate the net flux for this Gaussian surface, and this is the phi here. Okay, so here it tells you that on the left side it is epsilon naught is a constant multiplied by this phi will be the charge enclosed by this Gaussian surface. OK， 所以它就是 Q enclosed 就是所谓的静电荷 net charge， 就是这个高斯面里面包住的静电荷，但里面可能有正有负的，那你就加总，可能正的跟负的抵消掉，然后在外面的不算，它是 enclosed 就是被这个高斯面包起来的电荷才算。Okay, so of course this is just a multiplication, so we cannot use it use it much. Okay, 就是这个式子只是一个乘法，就没有很好用。So here we also write Gauss law as this expression. Okay, so phi as we define in several pages later. So we have this is the net flux. So this is the surface closed surface integral. This is the closed surface integral for the definition of the net flux. And then this is E. Okay, so E times this net flux, which is a closed surface integral, will be equal to the charge enclosed by this closed surface by this Gaussian surface. Okay, so yeah, so here let's take a look at the figure, and then we can have some introduction. So here we try to define 4 different Gaussian surfaces here. We try to define 4 different Gaussian surfaces here. So we have S1, S2, S3, and S4, 4 Gaussian surfaces. Okay, so for the first one, for the S1 is referring to this one. Okay. So as I mentioned, the Gaussian surface is is only an imaginary surface. It doesn't necessarily to be exist. It doesn't necessarily to be a very symmetrical structure. It can be a very straight shape. Okay. 所以它可以很奇怪，所以它故意画一个凹凹凸凸的形状出来。Okay, so 这个是 S1. Okay, so inside this S1 we have a positive charge. We have a positive charge. So according to this one, or even for this one, As much as this S1 encloses a positive charge, which means its Q enclosed is positive, and then epsilon naught is also a positive value. This is positive, which means that this flux or this flux is also positive. So for S1, phi 1 is positive. Phi 1 is positive. Okay, so for the next case, S2 is this one. S2 is this one. Okay, S2 is this one. Okay, of course you should consider this is a whole. This is a single figure. Okay, which means that in the space we have a positive charge here and a negative charge here. So when we consider S1 we have a positive charge, the negative charge is also there. Okay, but this negative charge is outside this S1. Okay, so in that case, when we consider S1 for the phi 1 Q enclosed, we doesn't count this negative charge. Okay, because this negative charge is outside the S1, outside of the S1. Here, when we consider S2, this Gaussian surface encloses this negative charge, but the positive charge is outside, so the net charge enclosed by S2 is negative. So here Q enclosed is negative for S2, this is positive, so which means that this closed surface integral is negative, or this phi 2 is negative. Okay, so S1 and S2, so here S3 is left side, this part is the S3. Okay, so in this S3 it encloses nothing. This positive charge and this negative charge are all outside. So the Q enclosed is perfectly zero. No any charge inside this S3. So in that case, Q enclosed is 0 for S3. Okay, so in that case, epsilon is a positive value, so it is not 0. So which means that this term must be 0. So then Q enclosed for S3 is 0. So we can see that phi 3 is equal to 0. Phi 3 is equal to 0. And for the fourth case is S4, which is the outer big one. Okay, in this case it encloses both the positive charge and negative charge. Here we assume these two charge has equal in magnitude but opposite in sign. Okay, so these two charge is equal in magnitude, 就是大小一样，符号相反而已。So in that case, the total charge enclosed by S4 is this charge added with this charge, so perfectly cancel. So the total charge enclosed by S4 is still 0. Okay, even though it encloses one positive and negative charge, but these two charges are perfectly cancelled. So the Q enclosed 4 or Q enclosed for S4 is also 0. In this case, phi 4, this integration for S4 is also 0. So here we also can conclude that S3, S4 are all 0. Okay, so here we just don't try to calculate any math. Okay, we just try to use this figure to let you know that, even though without any calculation, based on this Gauss law, we can easily observe that the flux of a given Gaussian surface is either positive, negative, or 0. OK， 就是我们可以知道这个正负号了，或者是0了。如果是真的要算的话，可能真的有一些具体一些的面啊，然后有一些具体的数字就可以算。这个就是只是一个示意图，让你们了解一下，就是这个高斯是怎么结算的。就是说，这个高斯面要包着那个电荷才会算在内，然后你把总的电荷放在右手边，那就代表说这个 flux 就是这个Q enclosed 除以这个 epsilon naught 啊 ，Q enclosed 除以 epsilon naught， 就是这个数啊，就会是这个积分啊，就会是这个积分。然后如果在某一些是对称的状况之下如果你这个 Gaussian surface 定义的好的话，它有可能这些全部 E 到 dA 都是一个常数，都是一个常数。那我们就反向操作的话，就是说 E 到 dA 是一个常数，所以它们就是乘起来等于某一个数。那我们知道了，那我们就除回去，刚才我们的操作是，我们尝试把这个 integration of E 到 dA 算出来但是现在我们如果真的要用这个高斯定律的话，就是我们反向操作。我们假设说我们定义好一个好的那个高斯面，那我们就知道它包着什么。那 Q enclosed 除以 epsilon naught 就是一个能够很容易算出来的数，然后我们就知道这个积分等于那个数然后我们再如果这个积分很容易算，它是一个乘法，就是它是一个固定的电场乘以这个表面积的话，这个高斯面的表面积的话那就等于那个数，然后就除回去，然后我们就求出来电场，就是这样一种想法。后面都是在做类似的事情，是这么利用那个 Gauss law。所以 Gauss law 的话，它的数学就会复杂，就是你要明白有一个这样的东西，就是一个面积分。我们不会算得很复杂，但是如果你利用这个面积分这么复杂的一个数学，就是一个多变数积分的一个数学之后，我们剩下就算一些乘法、除法就好了但中间也可能有一些加法、减法、四则运算。Okay, so here, so on this page, it tries to tells you that so the Gauss law is actually compatible to Coulomb's law. Okay, it can get the same result as the Coulomb's law. So they will say they are compatible, 就是它们是相容的，它们是可以得到一个共同的结论的。Okay. So here, suppose we have a positive charge Q here, and then we try to define the Gaussian surface to be spherical, 就是一个球体，然后它的圆心在这个电荷的地方。Okay, so in that case, here we have a Gauss law to be this part equals to this part is the Gauss law. Okay. So here we try to simplify this closed surface integral. So for this closed surface integral, according to what we learned before, okay, so the E field is always pointing outside. Okay, of course going through the charge, and then pointing outward. Okay, for example, something like this for different direction. We will have E pointing outside. And for each point, okay, so for every small element, we also can define dA. We also have dA. Yeah, also perpendicular to that element and then pointing outside. Okay, so we have a dA, something like that. Okay, so we can quickly observe that this E and dA are all pointing to the same direction, which means the first step is that E dot dA will be E times dA. Okay, of course there will be cosine of theta, but we simply observe that all this theta will be 0 degree, which means cosine of 0 degree is 1, so E times dA times 1 will be E times dA. Okay, so cosine of 0 degree, so this is nothing but 1. Okay, so we have a E dot, it becomes E times dA. Okay, and also we can observe that E are all constant, okay, because E are just related to the distance from the point to the charge, okay. But on the spherical, all of them are the radius. All of them are radius to be a constant, which means that E is also a constant. E is also a constant. So in that case, E can be put outside because we are integrating a constant. A constant can be put outside. It's just a multiplication. So here we try to put this E outside this integral sign. So it turns out to be the closed surface integral for this sphere， 就是一个球体的面积分，那就是球面的面积嘛，啊，所以这个就是球面的面积。球面的面积的话，就是高中的几何应该学过吧 ？Okay, so for the surface area of a sphere will be 4 pi r square 啊 ，will be 4 pi r square 啊，面积就是4 pi r 平方嘛，体积的话就是4/3的派 r 立方嘛，就是这个应该要记得一下。So this is the surface area of a sphere to be 4 pi r square. So we can put this one there. Okay, after putting this 4 pi r square there, we have epsilon naught E times 4 pi r square, and then equals Q enclosed. Q enclosed is actually this Q. So finally, we can just put this and this to the right side. Okay, so the left side remain E, and then we have a 4 pi epsilon naught here. So putting to the right side will go to the denominator. So we have this 1/4 pi epsilon naught, which is the K here, and then Q enclosed is here, and then we still have this R square putting there. So this is actually what we can get from the Coulomb's law. Or you can say, oh, Coulomb's law is something like 1/4 pi epsilon naught, and then Q enclosed times Q0, something like that. Okay, and then E will be F over Q0. So it turns out to be this one. So you can also say this one is the Coulomb's law. Yeah, so which means that if we have the Gauss law as the assumption, and then we have, for this case, we apply Gauss law for this situation, we can really get a result that is the Coulomb's law. So we will say the Gauss law and Coulomb's law are compatible to each other. Okay. 然后一个要注意的是，它们是定律啦，所以定律的话是没有办法证明的，所以你不要问啊，怎么证明这个高斯定律是正确？那高斯定律距离现在的话是多久啊？那个应该是19世纪的，19世纪18几年的距离现在多久啊？100多年了，100多年没有找到一个违反它的状况，所以就是没有办法推翻它啊。如果你找到一个反例的话，你就可以推翻它，就是一个定律的一个逻辑，它就是这样，就是我写出一个是正确的东西，我没有办法证明我把它叫定律。如果你有本事的话，你就找出一个反例让我知道这个定律是错的，那你就可以推翻它。如果你推翻不了它的话，那就代表说它为之的正确。Okay, so this is the relationship of Gauss law and Coulomb's law. Okay, so here we have a simple sample problem. Okay, so here it says in a cross section, a plastic spherical shell with a uniform charge Q equals -16 E and radius R equals 10 cm. A particle with charge Q is +5 E is at the center. Okay, so this is the Q, this is a small q, 5e. Okay, so this is equal to plus 5e. And then this capital Q is this one is a -16e. Okay, and then for this radius is R equals 10 centimeter. What is the electric field at point P1 at radial distance R1 equals 6 cm. Okay, so this is R1. This is R1 to be 6 cm. And then the radius of this sphere is 10 cm. 10 cm. So it asks you the E field at P1 here. Okay, so here we try to draw assume a Gaussian surface or draw a Gaussian surface, something like this. Okay, so this is the Gaussian surface for this part. Okay, so in this case, you just draw this Gaussian surface to here, and then inside this Gaussian surface, we only have this Q. And this is the point. This is the point P1. This is the point, or I draw it like this. This is the point P1. This is the point P1. And actually, this outside sphere is symmetrical, so we will assume the influence of the outside sphere on this surface is symmetry. And also this Q to this Gaussian surface is also symmetry. Okay, so we don't actually need to draw this sphere for this figure. So in such a way, we can consider that this Q will generate E field pointing to the right side, and also for this sphere at this point we have dA also pointing to the right side. So in such a way, we have the Gauss law like E epsilon naught integration of E dot dA equals Q enclosed for part A. Okay, so epsilon naught. Okay, so just as what I mentioned here. Okay, so this integration is symmetry. So and then E and dA are pointing to the same direction. So this dot product become a simple product, and then E is constant. So this E can be putting outside. So similarly, we can do the thing like this. Okay, integration of dA, and then equals for this part A, the Q enclosed is nothing but Q. So we only write Q here, and then this is a sphere. So this surface area is 4 pi r. Okay, so this is a 4 pi r for this surface area. Okay, so actually what we get is actually 1 over 4 pi epsilon naught times r square. Q over r square. So okay, so actually we can just plug in the numbers. So this is 8.99 times 10 to the 9th power, and then times Q is what? Q is E. Q is 5E. 5E means it is 5 times 1.6 times 10 to minus 19 coulomb. Okay, and then over R is that is actually R1 square. So R1 is 6 centimeter. So 0.06. Okay, we need to convert it back to the SI unit. So you need to pay attention. If it is centimeter, you need to convert it to 0.06 meter. Okay, so this is actually 2 times 10 to the negative 6 Newton per Coulomb. Okay, and then last time I already mentioned that 10 to negative 6 you can write it as 2 micro Newton per Coulomb. Okay, so you either answer one of them will be okay， 就是你喜欢用乘以10的多少次方也可以，你喜欢用这个 scientific prefix 也可以，就是选其中一个就好。Okay, so this is for question A, and then for question B, it asks you the same thing but at point 2, P2. P2 is actually outside. P2 is actually outside. So here we try to define the Gaussian surface here. The Gaussian surface for question B. Okay, so this point is P2. Okay, here we have Q, we have this big Q, and then also we know that this Q, this is a charge to this surface is symmetry. This sphere also symmetry. So we will assume that all the E field are uniform in magnitude over this whole Gaussian surface. So in this case, we can have similarly epsilon naught integration of E dot dA equals Q enclosed B. Okay, so here we have epsilon naught and then E and then integration of dA, which will be 4 pi. This is R1 square. Okay, so okay, maybe this one should be R2. In the figure, it is R2 is written there. So this one should be R2 square. And for the Q enclosed, we actually have both small q and big Q. So this is Q, this is Q plus big Q, which is 5e minus 16e, which is negative 16e. Okay, so finally we have E to be 1 over 4 pi epsilon naught, and then negative 11e, and then over R2 square. Okay, so we can just plug in all the number 8.99 times 10 to the 9th power, and then times negative 11, and then 1.6 times 10 to minus 19 over, this is 12 cm, so 0.12 square. Okay, so the value will be negative 1.1 times 10 to the negative 6 Newton per Coulomb. Or you can write it as negative 1.1 micronewton per Coulomb. Okay, so we can very quickly so actually we can just